Formation evaluation, in its broadest sense, ranges from the macro scale of a geologic basin mapped from satellite imagery to the micro scale of a pore throat examined through a scanning electron microscope. Whether at these extreme scales or somewhere in between, as in this well bore, the principal objectives of formation evaluation are to determine the size, the shape, and the lithology of a reservoir, and to characterize reservoir properties such as porosity, permeability, and fluid composition.
Welcome to our series on wireline logging. In this introductory module, GL401, we'll concentrate on fundamental downhole logging techniques and practices and see how they apply to formation evaluation. In Unit 1, we'll look at field equipment and general practices used during a well logging survey.
In Unit 2, we'll look at what logs can tell us about rocks, fluids, and conditions near the borehole.
But first, let's place wireline logging in perspective with other formation evaluation techniques.
As discussed in your manual, wireline logging is the common meeting ground for many diverse formation evaluation techniques. For example, geologists use wireline data, such as dip meter logs, to confirm or refine structural interpretations made from broad area imagery and outcrop studies. Geophysicists use downhole acoustic logging techniques to determine velocity profiles in an area in order to calibrate and accurately interpret seismic surveys. And engineers use a variety of logging techniques to design completion programs and estimate the composition and recoverability of reservoir fluids.
During the remainder of this module, we will emphasize open hole logging. For discussions of wireline devices used primarily in cased hole and production logging, you should rely on your manual. But keep in mind that wireline logging techniques can be used throughout the life of a well, from the time the well is drilled through its entire testing and production cycle, even to determine its depletion and point of abandonment. Let's begin Unit 1. We'll begin learning about wireline logging by going into the field and observing logging equipment and practices that are commonly used in open hole formation evaluation. Logging operations are conducted using wireline logging units. Two general types of logging units are in common use.
One is a skid-mounted immobile unit permanently attached to an offshore platform or used at a remote land location. Its primary function is to service that particular drill site. The other type is a truck-mounted mobile unit, which is generally assigned to a field dispatch office. Its primary function is to service the local onshore area. There are 6 basic components common to both offshore and onshore logging units. These components are a suite of logging tools, a multi-conductor logging cable, a winch mechanism, a winch control panel, computer recording and processing equipment, and support capabilities. A suite of commonly used downhole logging tools is present at the unit. In addition, special purpose tools such as sidewall coring guns and formation fluid testers may be on hand. A multi-conductor logging cable serves to physically and electrically connect the logging tools with a logging unit. The cable attachment mechanism, shown here, or head as it is called, is also designed to be the downhole weak link or break point of the cable system. Should the tool string become stuck in the hole, this weak link is designed to break before the cable snaps, avoiding costly fishing jobs for wireline. The winch mechanism is used to lower and raise the cable and attached logging or sampling tools into the well bore. A winch control panel measures the amount of tension on the cable and operates the winch at optimum speeds for various logging tools. Also, the tools can be positioned at precise depths for necessary tests and measurements. The computer is vital for receiving, viewing, and adjusting downhole tool responses, for storing and manipulating data, and for recording field logs. And finally, support capabilities, such as a generator to supply electrical power to the unit, a darkroom to develop log film, and reproduction facilities for making field copies of logs are considered standard equipment. In some units, satellite communication equipment is available that transmits log data directly to oil company offices, or, if required, to regional processing centers for further interpretation.
An open-hole logging survey can be thought of as consisting of 3 phases. The first phase includes mobilization of the logging unit, on-site rigging up, and field calibration of logging devices. The second phase is the logging phase, during which tools are run and the system is adjusted to hole conditions and previous logging runs. Logging measurements are taken during this time. The third and final phase concludes the survey and comprises on-site after-logging calibration and rigging down. The preparation of the field prints and well site interpretations must also be completed. Remember, as we discussed these phases in Unit 1, each phase can carry its own set of costs for the well operator. And, as with all drilling services, these can vary with supply and demand of equipment and the general economic climate of the industry. To get a feel for on-site logging operations, we'll travel along with a typical onshore truck-mounted unit while its crew conducts an open-hole logging survey.
Usually, the oil company representative calls a week or so before a logging unit will be needed to place the service company on call. At this time, all pertinent information regarding the well and type of surveys needed is given. Essential information includes hole diameter, total depth to be logged, and peculiarities of downhole conditions, such as the type of drilling mud or a deviated hole. Knowledge of these on-site factors is often critical in determining if special equipment will be needed at the well site. At this time, the oil company representative and the service company will often agree upon the amount of lead time required to notify the service company prior to logging. In remote and offshore areas, the logging crew may already be on site, depending on the type of service contract negotiated with the oil company representative. The objective of the notification is to provide adequate mobilization and setup time for the logging crew, and to minimize idle time either for the service company or the rig crew. At the time of notification, the oil company representative should again review the tools that are scheduled for the logging survey and update any well site conditions that may affect the survey. When notified by the dispatcher, the logging engineer and crew prepare the unit at the field office for the specific logging survey. The unit will bring the tools required for the necessary runs. These tools will have already been shop tested and calibrated to standard responses during a master calibration. These calibrations are performed periodically, according to service company requirements. For example, the induction tool shown here was shop calibrated by several tests. Based on tool measurements obtained from these tests, the uncalibrated induction responses of this specific tool were then mathematically adjusted to produce standard readings. All test results and calibrations are included in the shop summary shown here and are made part of the permanent record of the induction tool.
You'll learn more about industry standards and how each type of logging device is calibrated in GL 402, Well Logging Tools and Techniques.
As loading of the logging unit continues, radioactive sources for nuclear logging tools are transferred from their secure storage area to a secure carrying compartment in the truck. If sidewall coring is a possibility during the logging program, these explosive-bearing tools are also taken from their storage area and placed in the unit.
When the logging unit is fully loaded and the well site and time of departure are confirmed with the dispatcher, the logging unit will leave for location.
It is the logging crew's responsibility to find the drill site and be at the location at the specified time. Under certain conditions, special equipment may be situated at the well site to ensure that the logging unit can be brought onto the lease. The preferred location for setup and logging is for the logging unit to be in a backed position, beyond the pipe rack, and accessible to the end of the catwalk, with an unobstructed view of the rig floor. This location provides the logging crew with a workspace needed to lay out, assemble, and test the logging tools. It places the logging truck and winch operator in favorable alignment with the derrick floor and allows the visibility of all personnel throughout logging operations. As shown here, rigging up includes laying out the logging tools, testing the cable head and cable, testing the logging tools, checking out the surface equipment, and making routine checks of mud properties. As logging devices are assembled together and the string of tools is made fully operational, a before-survey calibration check is made. This confirms that any changes in tool responses from the shop calibrations are within allowable limits or can be explained. For example, nuclear devices like this neutron density tool are tested with and without the calibration jigs designed to produce a predetermined tool response. Still other devices use built-in calibration tests, like the internal resistors in this resistivity tool. All before-survey calibration check data are added to the permanent records of each individual logging device and are included in the final printout of the logging survey. Once the drill pipe is clear of the rotary table, the next step is to rig up. This procedure includes hanging the sheave wheels, threading the cable through under the bottom wheel and over the top wheel, then attaching the cable head to the uppermost tool and raising the tool string. A cable tension gauge is always used and may be attached to either the upper or lower sheave wheel.
It is important to remember that these sheave wheels will be points of maximum stress during the logging run. Care should always be taken to see that they are well secured. Final steps in rigging up can now begin.
The tool string is raised in the derrick and suspended over the hole. At this point, the well's depth reference, or 0 point, is set into the cable depth measurement systems. As noted in log headings, this reference point is usually the Kelly bushing, but may be the derrick floor or any point selected by the oil company representative.
You'll learn more about this and other log heading information in GL 402. If the survey includes a radioactive device, the last step in preparing to log is now taken.
The rig floor is cleared of any non-essential personnel, and the radioactive sources are placed in the tool. The hole should be covered during this procedure to ensure that the sources do not fall into the hole. After the sources are inserted, the tools are lowered into the hole.
With all logging devices now tested and operational, the logging phase can begin. At this point, we need a word about depth determination. This process involves more than simply lowering the tools to total depth and reading the depth on the meter. Service companies use certain procedures to ensure that the depth reading is as accurate as possible. Check with your service company for an explanation of their particular procedures.
Now, as the string of the logging tools is lowered into the hole, the logging engineer again tests tool responses. Often, benchmark lithologies like salt or anhydrite are used to confirm that accurate readings are being obtained. Once the tool is on bottom, the logging run can begin. Usually, logging is done in the uphole direction. This procedure is used in order to maintain a constant logging speed and good depth control, and in some cases is required by tool design. Sometimes, in problem holes, logging going down the hole may ensure that some data is obtained in case problems are encountered. The speed at which logging is carried out depends on the logging tools in the string. Each tool has a maximum speed at which it can be run. In general, the slower the tool is run, the better, although, of course, practical aspects such as the cost of rig time must be taken into account. The whole condition, tool design, lithology type, and concern for quality data should be the predominant factors in determining what the logging speed should be.
If you are not familiar with the various logging tools at this point, don't worry. You'll learn more about them in GL 402. Now, let's look at the logging run in more detail. Nowadays, for convenience, the repeat section is logged first, close to TD, which is usually near the zone of interest. Logging this repeat section is essential for documenting that the logging tools are operating normally and producing repeatable results. Repeats are usually run over the zones of interest so that a quick log is available for analysis. Sometimes it's advisable to run short repeat sections over anomalous intervals to ensure that the tools are operating properly. It is during the repeat survey that the logging engineer generally confirms that measurements being taken by the different logging devices in the tool string are plotting on depth. As you can see by looking at this tool string, numerous detector points are located throughout its length. No two devices are logging the same depth at one time.
In order to adjust this sequencing of detection so that all measurements for one depth plot together, data from all upper sensors are stored and fed back into the log plot when the lowermost sensor crosses the point being measured. This log plot is displayed in real time on a monitor within the logging unit. For the on-depth check, the logging engineer verifies that proper displacement to one common depth point is valid. This is done by comparing all curves at lithology breaks to determine that they show lithology changes at the same depth. If not, the logging engineer makes any necessary adjustments so that on-depth plotting occurs. After logging the repeat section, the tool is lowered to bottom, and the repeat section log is examined. Now a final depth check is made, and with the repeat section in hand, the logging engineer gives the go-ahead for the main survey to begin. Throughout the period of uphole logging, the oil company representative may sit with a logging engineer and evaluate initial logging results. The curves are compared to reference logs from nearby wells to make stratigraphic correlations. And important initial evaluations of zones of interest may be made at this time. As the string of tools moves uphole and passes through possible prospective intervals, the oil company representative studies the evolving curves with the logging engineer, and, if necessary, asks for a rerun over critical intervals. As logging proceeds, a permanent record of digital data is made on tape, and a visual record of tool responses is made on film. At the end of the run, the film is prepared on board the unit, and further on-site evaluations can be performed. Digital data are often evaluated and integrated at the well site through quick-look computer programs on board the logging unit. When logging of the selected interval is complete and the logging string is brought to surface, essential steps still remain before the logging phase is considered complete. The logging engineer must check to determine that the logging tools functioned normally and responded accurately to downhole conditions throughout the run. A quality control scan of the logs is usually done to verify this. Additionally, the logging crew must complete the after-survey calibration check. This involves repeating many of the same calibration checks that were carried out before the logging tools entered the hole, and entering these after-survey results in the tool check summary of the final printout of the logging survey. Such after-logging calibration checks are needed to confirm that tools responded consistently throughout the run.
When both the oil company representative and the logging engineer agree that the logs are good and any anomalous measurements are satisfactorily explained, the run is considered complete. If the logging survey consists of a single logging run, downhole logging is now complete and rigging down can begin. Sometimes several logging runs using different tools or sampling devices will be carried out during the survey. In the procedure of before-survey calibrations, proper depth recording, repeat, logging, and after-survey calibrations are similarly carried out.
It is important to note that sometimes subsequent logging runs can be based on the results of the first run, as in the sidewall coring run being set up here. Therefore, it is essential that the oil company representative and the logging engineer communicate effectively with each other throughout the survey, and that accuracy and details are obtained on the initial field prints. It is possible to transmit logging data via satellite or facsimile machine directly to the oil company's offices. This can be done after the logging run is complete and permits staff geologists and engineers in their offices to approve a run, participate in the selection of sidewall coring and fluid sampling depths, and modify subsequent runs of a logging survey. Upon completion of the last logging or sampling run, rigging down proceeds in a manner similar to the reverse of rigging up. Any radioactive sources are removed from their devices. Logging tools are lowered back onto the catwalk, cleaned up, broken down, and racked for transportation back to the field office. Shiv wheels and accessory items are detached and stored in the truck, and the cable system is secured. Field prints are made for the oil company representative. The logging survey doesn't end when the logging unit leaves the well site. Activity may move to a log evaluation center, where final prints, and in many cases, second-generation logs, additional downhole evaluations, and graphic summaries are made by the logging company in its log evaluation facilities. If requested, final results from these evaluations can often be transmitted to the oil company office in less than 24 hours. Routine processing, however, can take from 2 to several days.
This brings us to the end of Unit 1. Please take some time to study the corresponding sections in the manual and work the appropriate exercises. That will prepare you to move into Unit 2 and our discussion of the downhole logging environment. We've introduced the basics of well logging. Now, in Unit 2, let's examine formation properties, resistivity and density measurements, and the downhole environment. As mentioned earlier in the introduction to this module, a major objective in formation evaluation is to recognize lithologic units penetrated by the borehole and to understand their reservoir properties. Let's look at a section of the borehole represented by this core to understand the parameters of interest.
There are 3 physical properties of this core that determine whether the reservoir it represents will or will not be commercial. These properties are the rock's porosity. Is there enough void space in the rock to hold an adequate volume of hydrocarbons? The rock's permeability. Can the hydrocarbons in the pores be produced at economical rates? And the rock's fluid content, or saturation. Is the recoverable fluid going to be largely hydrocarbons or mostly water?
We'll look individually at porosity, permeability, and water saturation to see how they are measured, and then evaluate how their mutual association affects reservoir characteristics.
Porosity, as indicated here by the symbol phi, is signified by a percentage and represents the volume of pore space divided by the total volume of the rock. Therefore, a rock with 12% porosity has 12% of its volume made up of void spaces. These pore spaces can be any size or shape. They can be relatively isolated or highly interconnected. Pore space in a rock depends on many factors. For example, porosity is dependent on how detrital grains in a rock are stacked together. As shown here in this generalized cubic stacking of spheres, grain stacking can be rather open, resulting in high porosity. Or stacking can be closer, as in this orthorhombic pattern, this tetragonal arrangement, or this rhombohedral pattern, and result in lower porosities. Although nothing has changed except the 3-dimensional stacking of spherical grains, porosity has decreased from about 47% in the cubic pattern to about 25% in the rhombohedral arrangement. Of course, these figures assume that the spherical grains are solid. If they have intragranular porosity, as shown here, the total porosity would be greater and represent the combined intergranular and intragranular porosity. Other factors that alter porosity include variations in grain shape and the degree of sorting. In the case of sorting, the poorer the sorting, the lower the porosity, since smaller grains may fill in the pore spaces between larger grains. Porosity may be greatly affected by such secondary features as cementation, which can decrease primary porosity in a detrital rock, or by features that increase porosity, such as dissolution or fracturing. Permeability defines the ability of a reservoir to permit the flow of fluids. It is measured in darcies or millidarcies and is represented by the letter kappa. A permeability value can be indicated, but not directly measured from well-logged data. Core analysis, however, can provide an actual measurement.
How is a permeability value calculated? Let's consider a uniform porous medium that is completely saturated with a single homogeneous fluid. According to Darcy's law, the volume of fluid flow per unit of time, Q, is equal to the negative of the permeability multiplied by the cross-sectional area multiplied by the pressure gradient and divided by the viscosity of the fluid and the length of the rock sample.
Therefore, the permeability is 1 darcy when 1 cubic centimeter of fluid flows in 1 second through a medium that is 1 square centimeter in cross-sectional area and 1 centimeter in length, under a pressure differential of 1 atmosphere per centimeter, where the fluid has a viscosity of 1 centipoise. Permeability is controlled by the size of the pore throats, the connecting passages between pores. Permeability often decreases with depth because compaction and cementation restricts or blocks fluid pathways, and therefore reduces flow rate. We will be discussing 3 types of permeability in this video: absolute, effective, and relative. When only one fluid, such as water, exists in the pores, its permeability is known as absolute permeability, K. When 2 fluids are present, such as oil and water, the permeability of the oil is known as its effective permeability, K sub O. The effective diameter of the pores through which the oil is flowing is reduced by the water, which adheres to the grains. Therefore, effective permeability is less than absolute permeability. And finally, relative permeability, K sub RO, is the ratio of the effective permeability of a given fluid to its absolute permeability. Standard curves plot the relative permeabilities of the 2 fluids as a function of water saturation. Thus, in a typical relative permeability curve, we see that at low water saturation, only oil will flow. As the water saturation increases, the relative permeability of the oil decreases until some critical level is reached, at which both oil and water flow. The oil flow continues to decrease and the water flow to increase as water saturation increases. At some level of water saturation, oil no longer flows and only water flows. Beyond this point, as water saturation increases, the flow of water within the rock continues to increase.
However, the amount of fluid flowing is not a direct effect of the relative permeability, as different fluids have different viscosities. For example, if gas and oil have equal relative permeabilities, more gas and oil will flow within the rock because of the difference in viscosity. For a more detailed discussion of these types of permeabilities, see the engineering module PE 405, Core Analysis.
Porosity and permeability aren't always directly related. A rock with high vulgular porosity can have low permeability because the pores are not well interconnected. Conversely, this dense rock of relatively low porosity and storage capacity can have a high effective permeability and transmit fluids rapidly because of interconnected fracture planes.
However, in general, the association between permeability and porosity can be approximated as long as we restrict our conclusions to comparable rock types. Qualitatively speaking, when porosity increases, so does permeability.
This chart shows the general relationship between porosity and permeability for many types of reservoirs, such as reefal limestone, oolitic limestone, sucrosic dolomite, intercrystalline limestone and dolomite, well-cemented sandstone, chalky limestone, and fine-grained friable sandstone. But to restate our initial point that permeability and porosity are not directly related, if we look at a permeability of 10 millidarcies on the plot, we can see that porosities range from less than 10% to over 30%, depending upon rock type. Therefore, when taken alone, a porosity or permeability measurement won't necessarily provide an accurate approximation of the other. The amount of a given fluid in a rock is known as its fluid saturation. Since pore spaces are considered to be entirely filled with fluid, the total fluid saturation is always equal to 1, or 100%. In a three-phase system, the composition of reservoir fluids consists of a percentage of water, plus a percentage of oil, plus a percentage of gas. Fluid saturation is represented by the symbol S and expressed as a percentage. Therefore, total fluid composition is S sub W plus S sub O plus S sub G equals 1. The notation that S sub W equals 0.45, as shown here, means that the water saturation is 45%. Consequently, hydrocarbons make up the remainder, or 55%, of the pore space fluids. During log analysis, you might see such expressions rearranged to show hydrocarbon content as hydrocarbon saturation, S sub Hc, equals 1 minus water saturation, S sub W. This reservoir shows an oil-water contact. In a formation where the clay content is negligible, we might expect to see a low water saturation within the oil portion of a reservoir, while below the oil-water contact, water saturation would approach 100%.
It is essential to note, however, that the water saturation percentage determined at any point in a reservoir will not necessarily be the percentage of water recovered with hydrocarbon production. This is a critical factor in wireline log and reservoir evaluation. Let's look into it further. Many petroleum reservoirs are water wet. Initially, reservoir pore spaces were filled with water, and later, hydrocarbons migrated into the reservoir to displace the water. The result is water-wet surfaces, but primarily hydrocarbon-filled voids. As we discuss more completely in the manual, this subsurface condition causes both water and hydrocarbons to be present in different proportions and with different recoverabilities.
The first factor that causes oil and water to mix takes effect when hydrocarbons migrate into a reservoir. The formation water is displaced, and the surface tension of water across the pore throats is too great for capillary forces to force the water out. This means that in water-wet reservoirs, there will always be a certain amount of formation water trapped and retained along rock surfaces. The saturation of this trapped water is known as the irreducible water saturation, S sub Wi. Irreducible water will plot like this on a water saturation curve in the reservoir where oil is a continuous phase. This water will not move when the reservoir is produced, and, therefore, will not show up in the produced fluid. The general association is, the lower the porosity of the rock, the greater will be the saturation percentage for irreducible water. The second factor that causes oil and water to be mixed in a reservoir is capillary action at the oil-water interface. Capillary forces within the pore spaces cause the formation water to move up into the oil column. Once equilibrium has been reached, a transition zone has been established. In laboratory tests, the smaller the capillary tube, the more effective the capillary action and the upward movement of water. Therefore, we would expect the transition zone generally to be thick in reservoirs with small pore throats, and thin where pore interconnections are large. The percentage of water that will be recovered from the transition zone depends upon the relative permeability of the reservoir rock to the combination of water and hydrocarbons that is present. Near the top of the transition zone in a water-wet reservoir, hydrocarbons will make up a higher percentage of the produced fluid. For example, as water saturation increases in a water-wet rock, it is easier for the water to move than it is for the hydrocarbons. As water saturation reaches 75%, the relative permeability to oil nears zero, and no hydrocarbons will be recovered. The remaining hydrocarbons are referred to as the residual hydrocarbon saturation, S sub OR. As stated earlier in our definition of relative permeability, when residual hydrocarbon saturation is reached and 100% water is produced, the relative permeability of the system to water is not 100% of the absolute permeability. In this case, relative permeability is 40% of absolute permeability. You can also note that in an oil-wet system, oil-water relative permeability follows the same pattern as that for a water-wet system. However, it starts with a lower irreducible water saturation and has a greater relative permeability to water as residual oil saturation is approached.
With this background information, it is time to discuss how logging tools can obtain the necessary information so that we can properly evaluate formations. Now, no single logging tool can precisely identify the lithology of a formation or directly measure its porosity, permeability, and fluid saturation. However, by combining measurements from different logging tools, it is possible to solve for these critical variables. For example, two important measurements that can be made by logging tools are electrical resistivity and apparent rock density.
Formation resistivity, R sub T, is important because it is inversely related to water saturation. For example, in the uninvaded zone, all other things remaining equal, as the electrical resistivity of the formation decreases, the water saturation increases. Consequently, from changes in resistivity measurements, we can determine changes in water saturation, and therefore changes in hydrocarbon saturation. Density, indicated by the Greek letter rho, is important because it is inversely related to the porosity of a formation. In a given formation, as bulk density decreases, generally porosity increases. Therefore, if we measure the bulk density of a formation, we can estimate the porosity of that formation.
If you keep in mind the concept that formation evaluation generally solves for variables by combining a number of logging measurements, it should be apparent why we place a number of logging devices together or run them sequentially, and why we make interpretations from well logs that display measurements from more than one logging device. Now let's examine the borehole and the downhole environment in which logging tools operate.
As drilling proceeds and the borehole is extended into the earth, the drilling process alters the conditions surrounding the borehole. These conditions, in turn, will affect logging tool response.
In some cases, the effects of drilling can indicate formation properties. For example, if drilling mud filtrate penetrates a formation easily, a logging tool sensing this effect could be qualitatively indicating good permeability. In other cases, the effects of drilling with regard to log evaluation can be detrimental. For example, when the drilling process has created an irregular borehole, or the filtrate has penetrated deep into the formation, some logging measurements can be erratic, insensitive, or difficult to interpret. To characterize downhole conditions for logging purposes, the borehole and surrounding formation are generally envisioned to consist of 4 concentric zones. The first zone is the borehole with its mud and mud cake. The second is the invaded or flushed zone, where the mud filtrate has combined with mobile formation fluids. The next is the transition zone, where only partial invasion and flushing of formation fluids has occurred. And the fourth is the undisturbed or virgin zone, with its unaffected pore fluids. Of course, it is the analysis of the natural formation fluids in this outer, undisturbed zone, which more closely resembles the potential reservoir, that determines the presence of hydrocarbons. However, should hydrocarbons be present, the changes induced by drilling fluids in the altered zones are what indicate whether hydrocarbons are qualitatively movable.
Tools that measure the fluid content of the formation and record resistivity and conductivity have different depths of investigation. Therefore, it's possible to evaluate different zones separately using the Archie equation.
Applications of the Archie equation will be discussed in detail in the next module on well logging, GL 402. But for now, let's introduce the symbols for various properties of the four zones.
For example, the diameter of the hole is designated D sub H. The diameter of the invaded or flushed zone is D sub I. And the diameter of the transition zone is D sub J. Thicknesses also receive symbols, such as the mud cake, H sub MC, and the bed being logged, H. If we use this same downhole setting and look only at fluid saturation, we'll see that another set of symbols is needed. S sub XO represents the water saturation of the invaded zone, and S sub W is the symbol of water saturation in the uninvaded zone. If we look at the electrical resistivity properties of some of these same fluids in different zones, other sets of symbols come into use. The symbol R sub M represents the resistivity of the drilling mud. R sub MF, the resistivity of the filtrate. And R sub W, the resistivity of the formation water. Additional symbols are used for the resistivity of the mud cake, R sub MC, the invaded zone, R sub XO, and the resistivity of the undisturbed formation is represented by R sub T.
The variety of symbols you have just seen should give you a fair idea of the types of variables encountered in wireline logging and formation evaluation. You'll deal with these variables many times over when you apply the Archie equation to the various zones in GL 402.
In that module, we'll go on to examine the logging tools themselves. Specifically, we'll look at those tools that measure either a formation's electrical properties, acoustical properties, or nuclear properties.
In GL 403, we'll see how data from various logging tools are combined to produce logs that evaluate specific formation and fluid properties. The final module in the series, GL 405, will be devoted exclusively to dip meter interpretation.
What have we covered in this introductory module? We followed a logging unit out to a well site and observed the mechanics of logging a well. We've examined three physical properties of a formation that well logs indirectly measure: porosity, permeability, and fluid saturation. We've introduced two important measurements that can be made by logging tools: electrical resistivity and apparent rock density. And we've looked briefly at the borehole environment in which tools operate. Take time now to read your manual and study these topics. See you in the next module, GL 402, where we'll look at specific logging tools.
This program has been sponsored in part by the following companies: Agit, Aramco, Chevron Corporation, Mobil Oil Corporation, OxyCities Service Oil and Gas Corporation, Petro-Canada Incorporated, Phillips Petroleum Company, Schlumberger Limited, the Shell Companies, Texaco Incorporated.
and for the other lines. Then, provided all the time values are harmonious, we contour them to show the highs and the lows.
This, then, is our time structure map on the chosen horizon. On this, we estimate the possible oil-water contact and decide where to drill.
We remember also that the operation of following a particular horizon on the seismic section is called picking.
So there are 4 basic operations in structural seismic interpretation: picking,
To identify and follow the horizon to be mapped,
timing,
to measure the reflection time from datum to the picked reflection,
posting,
to transfer the measured reflection times to the map,
and contouring.
to show the structure, the relief, and we hope the closure of the chosen horizon.
Picking, timing, posting, and contouring.
From the section to the map. Well, what do you think? Picking, timing, posting, contouring, it all seems rather a mechanical process, doesn't it?
I could do that.
Yes. In fact, we shall find that 2 parts of the process, the picking and to some extent the contouring, are often far from mechanical. To do them well needs all the world's knowledge of how the Earth is and how it got that way. And even then, we're often not sure that we have it right. And that's why seismic interpretation is interpretation rather than data reduction. But in this course, we always try to start simply, to establish the principle, and only then to consider the complications. So let's take as our first example a case which is almost mechanical. Let's just take a reflection. We'll ask nothing about the geology that created that reflection. To us, it will be just a surface down there somewhere in the Earth, and all we shall do is to map that surface mechanically. Much of what we're going to do is done nowadays at an interactive computer workstation. But we're going to do it by hand this time, to get a good feeling for the operations involved. Now, what do we need? The shot point location map, which tells us where the lines are. A large wall. The sections themselves, of course. A large table on which we can spread out the sections. Good lighting. For a long day of this can be hard on the eyes. Some fine colored pencils and a large eraser. There's a message in that. In interpretation, we do a lot of discarding, a lot of testing, of checking various interpretation ideas against the data, and of seeing which ones do not fit, discarding them. Oh, we do a lot of discarding. Let's look at the map first. This is the way it really is, but we'll thicken it up for the video.
There, that's better. Our grid of lines. Now let's see, the scale of the map,
1 to 50,000. So 2 centimeters on the map represent 1 kilometer on the ground. Easy.
and the shot points. 10 shot points to 4 centimeters.
Which is, let me see, 10 shot points to 2 kilometers, right?
Right.
The first section, line 1, looks pretty good. Plenty of reflections. For interest's sake, let's select a reflection with some relief. Here, this one. And let's map the surface represented by that reflection.
All right, let's mark the high from that section. On the map. There. Two-way dip.
Okay, now to line 2. There's the same feature with its turnover. There.
So to line 3. Same feature with its turnover. There.
And on the cross line, line 5. Yes, there it is again. There. Which gives us the broad picture. It seems that our reflection surface may indeed be a closed high. Perhaps somewhere here.
All right, then. It's worth doing the work.
Yes, the work. The grunt work, as we call it. First, we must mark the line ties on the sections.
Start with that cross line in the middle, line 5.
Okay, on line 5, shot point 7574 intersects with line 3, shot point 8155, more or less.
Line 5, shot point 7574, intersects with, hey, they've done it for us in the processing. Line 3, shot point 8155.
Great. Sometimes they do and sometimes they don't. And when they don't, then it's grunt, grunt, grunt.
Now there's more grunt. We take the dip lines, the ones across the feature, identify the line intersections, and start to fold the sections at the line intersections.
Carefully and vertically.
Yes, right down the trace.
Well, enough of that. Now let's get down to business. While we were looking at the sections earlier and during the grunt work, it was clear that this was a good place to start.
In general, start where the reflections are clear, continuous, and uncomplicated.
So let's start by working around this loop. The first side of the loop and the corresponding section within the loop. Now, where is the surface we were going to map? Ah, there it is. Then we take our fine-colored pencil and pick.
We make it fine, partly to give precision to the timing,
Partly to make it easy to erase.
but most of all because if we put too much color, it's difficult to decide later whether a different pick would have been better.
But for the sake of the video,
All right, for the sake of the video.
that's the first side of the loop picked. Now, to the second.
And here's the tie. The first line, then the second, folded at the intersection, joining the first at the right place. No doubt about that. The tie is good, and the pick is here.
That's the second side of the loop picked. Now, to the third.
The second, the tie point, and the third. Again, a good tie. The pick is here.
That's the third side of the loop picked. Now, to the fourth.
The third, the tie point, and the fourth. Once more a good tie. The pick is here.
That's the fourth side of the loop picked. Now we come to the moment of truth. Will the fourth pick tie with the first? The first, the tie point, and the fourth. Bravo, it ties.
Always, always check your picks around closed loops.
It gives us such a nice warm feeling when they tie.
Now, with one loop done, we can move to the next loop. We already have one side of it picked. The existing pick going east. The tie point, and the next line going north. The tie point, and the next line going west. The tie point, and the next line going south. The tie point, back to the original line. Again, it ties, it checks.
Good. Now we have closed the second loop. And so we continue, round the third and last complete loop.
Keeping our confidence high.
Yes. Where a piece of line does not form a closed loop, then we extend the known pick as best we can, but with our confidence not quite so high. Similarly, with this line. And finally, with this one.
That's the picking done. Very good. Now we go back to the grunt work, timing and posting.
Okay, you time and I'll post. Let's start on line 1.
All right, line 1 from the south end. Shot point 7961, 2.52 seconds.
Shot point 7961, 2.52.
Shot point 7958, 2.50.
Shot point 7958, 2.50.
Shot point 7956, 2.48.
Shot point 7956, 2.48.
Shot point 7953, 2.46.
Shot point 7953, 2.46.
Grunt.
Grunt. Grunt and more grunt. But eventually, when the timing and the posting are done, we can start the contouring, and that's much more fun.
First, we look for the trends. In this case, we check the axis of our high, those two-way dip symbols we put on earlier. So the axis is this way.
Then, with that as a guide, we look for a simple place to start drawing the contours.
There. That'll do nicely. Just rough them in at first. 2.48 is here and there. 2.46 is here and there. We're joining together all the points which have the same reflection time on all the lines. 2.44, 2.42.
Easy. 2.40, 2.38, 2.36.
Now we start to see what that eraser is for. Many of those could be improved. Yes, that looks more like a real surface.
A few more and we begin to see the rough shape of our high. And here is the apex.
Or crest.
Or culmination.
Then we indicate that the extreme contour is a high, lest anyone should think it's a low. Perhaps color it to make sure, and really feel quite pleased with ourselves. Notice, too, how on the north flank the contour lines are a little closer together.
Indicating steeper dip.
And on the south flank, they're further apart.
Indicating gentler dip. All right, now let's go to the map label. This is a time structure map. On the horizon, we picked in yellow, the yellow horizon. The contour interval is 20 milliseconds. And the datum is, in this case, sea level. Add the date.
All maps must be dated.
And the author.
Who was that doing the contouring? Could it be...
Well, yes, so it was. Good old George.
What is it, George?
He's telling us not to forget the cautions.
Ah, yes, so he is. First and foremost, this is a map in reflection time, not depth. So we remember that caution, that time maps can be distorted by velocity variations. In the near surface on land,
or by variation of the water depth at sea. So that's the first caution.
Right. The second caution is that since we were working with unmigrated sections, this is an unmigrated time map.
So that the apex is in the right place, but the high is not as broad as it appears from the map. The flanks are really steeper, and the closure smaller.
And the third caution is about that yellow horizon. To the geophysicist, the yellow horizon is something real and physical, which we can see. But to the geologist, a yellow horizon is meaningless. Is it a lithologic boundary, a time stratigraphic boundary, an unconformity, top Eocene, lower Cretaceous, or what? So we have to remind ourselves that all we're doing in this example is the strictly mechanical task of mapping a surface. At this stage, we are saying nothing about the nature of that surface.
But we are going to do more than this mechanical mapping later on, aren't we?
Indeed we are, but keep it in perspective. A great deal of seismic interpretation is still done to find structural traps on yellow horizons, or blue horizons, or purple horizons. Okay, let's take another example. Instead of mapping a smooth, unbroken surface, let's look at a faulted surface. This one. What would you say? A clear down to the east fault here?
That was too quick. Let me see it unpicked again. Ah, yes. Okay. I might disagree in the details.
Interpreters always disagree on details.
Yes, more or less. Then there's an antithetic fault there, too.
Here?
Well, all right, for the sake of peace, yes.
Suppose then, for an example, that this reflection is known to be associated with a good porous reservoir, and that this interval above is known to be a good sealing shale.
Then we have a potential fault trap. On this line, we have clear closure against the fault.
But, as always, we have to remember that one good section does not make a prospect. Before we start getting excited, let's check the other lines. On the next parallel line to the south, well, dip reversal, but certainly no fault down to the east. On the next parallel line to the north, however, there it is again, clear as a bell, and still with good potential as a trap. The antithetic fault, not quite so well developed here. All right, the next parallel line to the north, aha, much less pronounced faulting at target level now, more like a flex. So, on the next line further north, we'd expect little or nothing at target level. Well, what do you think?
I think we'd better map it.
So do I. First, as before, we transfer the major features to the map. In this case, the big fault. On line 3, it is at shot point 465. So, we go to line 3 on the map, and there draw the symbol for a fault, down to the east.
We don't know at this stage that the fault is perpendicular to the line. We'll find out later which way it goes.
Then, on line 4, again, the big fault, very clear, at shot point 1715. Again to the map. And mark the fault down to the east. And from line 5, the smaller fault down to the east.
So the fault is, more or less, north-south, curved but generally perpendicular to the lines.
Whoa, hold it. If, and only if, we know it is the same fault on all 3 lines. If not, it could be this.
But if it were that, we would expect to see faults on that north-south tie line, cutting it there, and there, and there.
Well, the north-south line is that.
And do you see any suitable faults on that?
No, I don't.
So I was right all along. The fault goes more or less north-south.
Yes, you were, this time. But you always have to check, and it's usually not as clear as in this simple case.
No, it is not. That's why we have a whole module later on fault interpretation.
All right, now let's map that yellow reflection. Looks to me as if the contour interval should be 20 milliseconds, and as if we can time on that interval. You call out the shot point numbers corresponding to every 20 milliseconds of reflection time, and I'll post them on the map.
Okay, starting on line 2. Shot point 1450, time 3.58 seconds.
Line 2, shot point 1450, 3.58 seconds.
Shot point 1495, 3.56 seconds.
Shot point 1495, 3.56 seconds.
Shot point 1535, 3.54 seconds.
Shot point 1535, 3.54 seconds.
Shot point 1555, 3.52 seconds.
Grunt.
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 Grunt. Oh, grunt.
You see why, nowadays, this chore is usually done on a digitizing table with a plotter to draw the posted map.
Or better still, at an interactive workstation.
Anyway, it's done. Now, we can contour. Let's start with a contour at 3.56 seconds. Then 3.54 seconds, 3.52, and so on. Mostly just regional dip. Ah, turnover. All right, so down there we'll have to go carefully. Before we tackle the tricky parts, let's just go on putting in the easy contours. Now that last one, 3.20 seconds, we can also find over here. So now we can take that contour up to the fault on both sides.
Which illustrates one of the interpreter's golden rules.
Contours which enter a fault must also emerge from the fault.
Now we can add a few more simple ones. Mostly regional dip again, giving us the general direction of the contours. Then, with some care, we project the remaining contours up to the fault. Each contour which enters the fault must also leave it. Somewhere in here we must add that antithetic fault down to the west, and probably a second minor one. Then, on we go, honoring these faults and the contouring in the same way. And the low, which never quite faulted. Now we can go to the north, entering the fault, leaving the fault, entering the fault, leaving the fault. Then the little high, unfaulted, and the final picture. After we're sure we have it right, at a fairly detailed contour interval, we can simplify the map by omitting alternate contours. And the message? A north-south anticlinal nose, faulted down on its east flank.
Pretty, but a bit fast. Let me just check it. On line 4, for example. As I look at line 4, I see the yellow reflection rising steadily from about 3.44 seconds near the west end to about 3.17 seconds at the fault. Then downthrown to about 3.29 seconds, then rising to about 3.20 seconds at the east end. Show me that on the contour map.
Line 4, near the west end, about 3.44 seconds, as you said. Then rising steadily, and steadily means equally spaced contours, up to 3.17 seconds at the fault. Then downthrown to about 3.29 seconds. And then rising to about 3.20 seconds at the east end.
Just like that old fellow said, isn't it? From the section to the map, from the map to the section.
Always check the contour map back against the section.
Now, where are we? Do we have a prospect or not?
Well, I'm afraid not. Looks to me as if, despite that beautiful appearance of a trap on some of the lines, there is no closure.
Right. Any oil or gas which may have migrated up this way has just gone on migrating around the north end of the fault and is long since gone. There is no trap, there is no oil, there is no prospect.
Phooey. And after all that grunt work, too.
This is a way of life for the interpreter. Many of the leads he sees on the section are discarded when they're mapped. The good interpreter learns to minimize the work he puts in on leads which are later discarded.
Let's take another example.
All right, let's take a reef.
Ah, yes, a reef. Often a valuable prize. Very porous, very permeable, an excellent reservoir. Beautiful, too.
Indeed, but in seismic section, reefs are very variable. Sometimes they're obvious. Just look at this one. No problem seeing that, even without having it colored in for us. Some reef, about 6 kilometers across, and would you believe 2 kilometers high? But other times, reefs can be very subtle on the seismic section. That one, for example. Surely we could have been forgiven for missing that one.
No, you're forgetting. The great petroleum club in the sky and the entry requirements. Remember, there is no forgiveness for missing a field.
Ah, yes. Well, how could we be sure of not missing a reef like this?
Hint. Look at the red reflection above the reef.
Okay, I see it. It has a small flex right above the reef. So you're suggesting that we map the time structure on that horizon?
No, that won't do. If we just make a simple structure map, that would also show all the structure due to other influences, like the regional dip to the left. Nope, much better to map the time difference between that reflection above the reef and some other suitable one. Either a reflection below,
So that the reef would show up as a local thick,
or a reflection above.
so that the reef would show up as a local thin.
The search for subtle reefs, therefore, is an excellent example of a much-used interpretational technique, the mapping of a time interval, rather than the mapping of time structure.
Let's illustrate it here. Somebody has found a reef, and we want to find another one. Tough going for a seismic crew. Cliffs, steep hills, and completely wooded. All we can do, if it's not to be too expensive, is to work in the valleys and along the roads. Accordingly, our seismic lines along the roads certainly do not form a regular grid. And one of our worries is that the reef which has been found would fit quite easily in some of the gaps in the coverage. In here, or here, or here. Now, in this case, the reef which has been found is not too subtle. It's not exactly obvious, but we can see it on the seismic section. And so, obviously, the first thing we do when we receive the new seismic sections is to scan them for anything which looks like this.
Suppose we find nothing. Do we give up? No, we do not. We start mapping a suitable time interval, which involves the reef in some way. Why? Because as we see, the time interval starts to change before we hit the reef. So on a cross line here, a slight thinning of the interval would tell us we were near a reef, even though we could not see the reef itself. So we take each of our new sections, no reef visible there, pick the reflections at top and base of the interval, and proceed all over the area.
And then we time the interval. This needs some care. Since the variations we're looking for are only a few milliseconds, we cannot afford to be, say, 2 milliseconds in error high on one pick and 2 milliseconds in error low on the other. So we go carefully.
And then, on the map of the seismic lines, we post the time interval values and contour them.
Now we're looking for the thins, the blue areas.
Hey, look at that. An open area with no lines across it, but all the lines around it showing slight thinning.
Interesting. Well, the first thing to do, urgently, is to get our land department busy and make sure we pick up all the open leases from the landowners.
Or, if there aren't enough open leases, go for a farm out.
Right. Then we need a new seismic line across this thin. What does the country look like?
Tough, I'm afraid.
Well, it's not urgent enough to bring in a portable crew just for one line. That would be expensive in mob-demob costs. But next time there's a portable crew in the area, we'll put in a cross-country line right across here, between the intersection of lines.
Well, that's what they did, and this is what they found. Another clear reef. Another victory for the technique of mapping a time interval.
There's a couple of other points we should make about time interval mapping. The first is static corrections. When we're working from the hills down into the valleys, we know we're at risk because of the fill, the low-velocity fill in these valleys.
I can see what you're going to say, that when we're taking the difference between two reflection times, we're less vulnerable to static correction problems.
Right. And the second point is the usefulness of time interval mapping in the search for many types of stratigraphic traps. The reef, of course, but also the sand-filled channel and the bar. In fact, any type of reservoir body which resists compaction more or less than its surroundings. Let's go back to the reef for a moment, and another example, a Canadian one this time. Here's the reef, all right. We can see it by eye. Why does it appear in two pieces? Well, probably the line goes across a re-entrant in the reef. Perhaps in a plan view, it is like this.
What a pity we cannot actually see this part of the reef. Probably it would look like this, an actual reef exposure. Closer and closer. There. What a reservoir.
In this case, the reef catches our eye because there are virtually no reflections within it, and because of the termination of reflections off the flank. So we scarcely need other indicators. But obviously, we could have found the reef by mapping either this interval, looking for a thick, or this interval, looking for a thin. In fact, this is the map obtained from the lower interval, where we're looking for a thick. And this is the map from the upper interval, where we are looking for a thin. Both maps establish the location and extent of the reef very well. But what would we do if the top of the reef does not show on a seismic section, and we did not have this reflection over the reef? Then we could still find this reef by time interval mapping over this interval. Why? Because there is a small but detectable fin at the reef. And why should that be? First, perhaps because of a slight high in the carbonate platform. That might be why the reef grew there in the first place. Or second, because the velocity within the reef is higher than that in the flanking rocks, causing a small velocity pull-up.
Well, what you've said is very significant, because now you're not being content with the strictly mechanical interpretation we've talked about so far. Now we're thinking as we go about velocity likelihoods and the compaction of sediments and the internal nature of reefs. We're beginning to introduce some real geology.
Exactly. Mechanical interpretation, picking reflections, timing, posting, contouring, can take us so far and no further. Mostly it takes us to structure, to the finding of structural traps. But seismic interpretation can take us much further than that.
First, it tells us about geological history. When we see an angular unconformity at outcrop, we know that the lower rocks were deposited near horizontal, were then tilted and eroded. The upper rocks were then deposited near horizontal, and in this case, the whole system was tilted again. Tectonic history. Seismic interpretation allows us to reconstruct such history deep in the earth. The lower rocks deposited near horizontal, tilted, eroded off, and new sediments beginning to be deposited on top, at the sea floor. An angular unconformity in the making, and then later, with the upper rocks well established on top. Unconformities, then, are the key to tectonic history.
Say it again. It's important.
All right. Unconformities are the key to tectonic history. And I'll give you an example. First, a thick uniform layer of salt, top and base parallel. Next, a layer of clastics, conformable, horizontal, top and base parallel.
The surface of deposition must have remained very stable.
Right. Next, another layer, same story. But by now we have a lot of heavy sediments sitting on top of all that light salt, an unstable situation. The salt starts to move, forming a pillow, with its apex to the left off the screen. At the left, the orange and gray sediments are pushed up and eroded, an unconformity in the making. At the right, the withdrawal of the salt allows those layers to sink. A new layer, yellow, is formed. This yellow layer thickens to the right, not because of erosion, but because of thickening during deposition.
Hold it a moment. That's important, too. Yes, when the surface of deposition inclines down because of subsidence, the new yellow layer thickens. That we see. By the same token, of course, when the surface of deposition inclines up because of uplift, the new layer thins.
Yes, but let's stick to this illustration.
Sorry.
So what happens next? Next, the apex of the salt moves to the right. At the left, this allows the unconformity to sag down, and the yellow sediments to fill up the hole. Next, the apex of the salt continues to move and swell to the right. More erosion. The swelling draws more salt from the right, allowing the rocks there to sink further, and new striped rocks to be deposited in the hole, onlapping the unconformity.
New rocks onlapping the unconformity? Oh, yes, I see. Okay.
Now all this swelling is too much for the orange layer, which cracks apart and allows the salt to rise through the fissure. The squeezing out of the salt allows the rocks each side to sink. The big sink is filled with new green sediments, much of them derived from the masses of broken rock uplifted by the salt. The salt continues to surge up. The area around it continues to sink, filling with the brown rocks. There is scarcely any salt left in the original salt layer. The movement stops, and the surface is eroded. Finally, a new layer, horizontal and parallel, is deposited on the unconformity. We have reached today. And today, there comes a seismic boat, which finds this.
Hey, that's a nice example. Let's see how you worked all that out.
Okay? First, mark the major unconformities. And then the other major picks.
All right, I agree with those, more or less.
Okay, in basic form then, that. Now we strip off the first layer by bringing its base, the unconformity, up to the surface. Then we strip off the brown layer by bringing its base up to the surface. Now we can see that the salt was a pillow before it surged up and broke through. Then we strip off the green layer, bringing its base up to the surface. Then we strip off the striped layer, bringing its base, an unconformity again, up to the surface. Then we strip off the left-hand yellow layer and some of the right-hand yellow layer, always the same way. And finally, the parallelism of the gray and orange layers tells us that they must have been deposited thus.
So, geological history by the study of a seismic section. From the parallelism of layers, from the thickening and thinning of layers, and in particular, from the unconformities.
Catch those unconformities. From them we unravel the geological history.
Next, seismic interpretation tells us something about the nature of the rocks. We're going to look at a seismic line all the way across a basin, a regional line. Here we are then at the left edge of the basin. As we go, keep your eye on this reflection.
The red one?
Right. What we see then is a strong reflection which is continuous right across the basin. Oh yes, it hiccups and stutters a bit here and there, but that same basic reflection extends across the whole basin. 250 kilometers of it, 160 miles.
Go back again.
What does that mean about the nature of the rocks generating that reflection?
That they are marine.
Yes, and?
That no sandstones are involved.
Right. Sandstones in their nature tend to be local, seldom basin-wide. The most likely candidates then are marine shales and carbonates. In fact, that reflection probably comes from the interface between a marine shale and a carbonate.
But if it's the sandstones we're after?
Well, the first place to look for sands, of course, is at the shoreline, at the basin margin. This, then, is the habitat of sandstones, where coarse sediments washed down from these mountains were dumped into the sea and sorted and rounded and reworked by the waves.
This concept of establishing the likely nature of the rocks from seismics is very exciting. We call it seismic stratigraphy, and it really is fun, very satisfying indeed. We'll talk about it in several other modules. But despite our fascination with seismic stratigraphy, we have to keep things in proportion. Most of what the interpreter does is still concerned, at least in part, with structure and with the mapping of structure. So the next few modules in the interpretation series are concerned with the skills of structural interpretation, contouring, fault interpretation, depth conversion, structural modeling. So, if you're a geophysicist, hang in.
This program has been sponsored in part by the following companies: Egypt, Aramco, City Service Oil and Gas Corporation, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation, Phillips Petroleum Company, Schlumberger, Standard Oil of California, Texaco Incorporated. IHRDC and the above-listed companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein, and the user, upon using this program, thereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise out of the use of this program. No portion of this videotape may be reproduced without the written consent of IHRDC. Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. Since this well has been proven productive, it is being cased and cemented. When the cementing operation is complete, it will be logged. This module on cased hole logging focuses on the geophysical logs that are run in such cased wells. You might expect to find this program among the modules on well logging within the geology specialty of IHRDC's video library. But it is located within the engineering specialty, because such logs are often run and evaluated by engineers. The main reason for cementing the casing in a well is to isolate and control the fluids and pressures present in subsurface formations. Unfortunately, while accomplishing these goals, a casing string also permanently prevents us from evaluating those same formations using many of the techniques employed by open-hole logging tools which can be placed against the wellbore wall.
So, if we want to monitor changes in reservoir fluid saturations over time, we need cased hole logging tools which can see through the casing and cement barriers we've installed. In fact, we may also wish to use cased hole logs to measure the quality and continuity of the cement sheath that we've placed between the casing and rock formations, or to inspect the condition of the casing over time. And once a well's casing has been perforated for production, we may also need to run cased hole logging devices to measure the relative amount of fluid being produced from any given zone.
Many of these cased hole logging devices are also termed production logs, since they are run during or after the well's completion phase, when the well becomes the production department's responsibility. The spectrum of cased hole logging devices can be categorized in several ways. First, as either small enough to be run through tubing or as having diameters so large that they must be run before tubing is installed or after it is removed. Through-tubing operations generally require a pressure containment system that permits the introduction and retrieval of the tool string while the well is under pressure or flowing. A discussion of this equipment is found in Section 3 of the Video Library module on perforating, PE 303. Cased hole logs may also be categorized according to their region of investigation, that is, whether they gather data from fluids inside the tubing or casing, from the wall of the tubing or casing, from the annular area between casing and formation, or from the formation itself. Some cased hole logs will sample more than one area and have primary and secondary zones of investigation. For example, temperature logs, noise logs, and flow meters primarily indicate fluid flow inside the tubing or casing, although such logs can also be used to detect flow behind pipe. Caliper logs, corrosion detectors, and the cased hole borehole televiewer are run only to investigate the inside wall of the casing or tubing. The various cement evaluation tools look primarily at the cement-filled casing formation annulus, and the various nuclear tools investigate the fluid saturation, porosity, and lithology of the formation itself.
In this module, we shall look first at the evaluation of the formation through the casing, focusing primarily on the pulsed neutron logs. And then in Unit 2, we shall cover the use of cased hole logs to evaluate the integrity of the casing and cement. Finally, in Unit 3, we shall look at the qualitative evaluation of fluid flow in and behind pipe. Now, since each logging company's specific services can't be examined in a video of this size, we shall discuss each device in a generic sense. We begin then with formation evaluation through casing.
Most of the devices used for formation evaluation through casing are nuclear in character, although acoustic devices are beginning to be used with some degree of success. We shall focus on the measurement of fluid saturations using pulsed neutron logs and carbon-oxygen logs, the measurement of porosity using compensated neutron logs, and the determination of formation lithology using gamma-ray logs and spectral gamma-ray logs. Presently, there are at least 5 varieties of pulsed neutron tools available commercially. Whatever tool is used, the principle of measurement is fundamentally the same. Within the tool, an ion accelerator is activated for a few millionths of a second, bombarding a target and creating a burst or pulse of neutrons. Since neutrons can easily pass through the tool, the tubing, and the casing, a cloud of neutrons is created within the formation. Initially, at high energy levels, the fast neutrons collide with the surrounding atoms, quickly reaching a lower level of energy comparable to the surrounding matter. This energy level is a function of the system's absolute temperature, and such neutrons are therefore called thermal neutrons. Hydrogen atoms, having only a proton for a nucleus, are of equal mass with the neutrons, and thus are more effective at slowing down the neutrons than a heavier atom of, say, oxygen or silicon. Of course, there are plenty of hydrogen atoms present in 2 common reservoir constituents, water and hydrocarbons. Once thermalized, the neutrons are easily captured by nearby nuclei, which then release a gamma ray. Of the elements prevalent in the reservoir, chlorine atoms are particularly good at capturing thermal neutrons. The measure of an element's neutron capturing ability is termed its capture cross-section, or sigma. Chlorine's sigma is 570 capture units to hydrogen's 200. Because the capture unit is based on a per gram of atoms basis, chlorine is actually 100 times more effective than hydrogen at capturing neutrons. This is significant because by monitoring the number of gamma rays emitted by the formation following a neutron pulse, we can measure the rate with which the neutrons are captured. This can give us an indirect indication of the relative amounts of high and low sigma elements in the formation. Since formation waters are often quite saline, having large amounts of chloride ions in solution, a rapid decline in the gamma ray count can mean a large proportion of chlorine and can imply a high water saturation. Unfortunately, oil and fresh water have almost identical capture cross-sections. So the use of a pulsed neutron log is restricted to formations having salinities above a certain minimum. Natural gas, on the other hand, has a capture cross-section only about half that of oil, So, with the right salinity-hydrocarbon relationship, the tool can distinguish gas, oil, and salt water. On the semi-log plot, we see an initially high count rate due to the large number of neutrons in or near the casing, especially if the casing is full of salt water. After a short time, a straight line decline in the count rate is evident. At later times, still only microseconds, the background gamma ray count rate is essentially constant. The straight line decline in gamma ray count rate is defined by the equation n equals n sub O times e to the negative t divided by tau, where the number of gamma rays observed at time t is equal to the number observed at the beginning of the decline times the constant e to the negative power of time divided by tau. This constant tau is measured in microseconds and is inversely related to the capture cross-section of the formation, where tau equals 4,550 divided by sigma. So determining the slope of the gamma ray capture rate decline curve, we determine the formation sigma. If we independently know the formation porosity, lithology, and water salinity, we can calculate the relative amounts of oil, gas, and water in the rock.
The primary difference among the various commercially available pulsed neutron logs is in the manner in which they determine the slope of the gamma ray capture rate decline curve. Some tools use measurement gates which are opened and closed at fixed times to measure the count rate and determine the slope of the curve. Others have gates which slide back and forth as functions of the capture cross-section of the formation, using a constantly self-correcting process to maintain the slope measurement on the straight line portion of the curve. Some have more gates than others. For the specific variations and important features of individual tools, you should ask for an explanation by the appropriate vendor representative. For our purposes, we shall continue with a description of the typical display of sigma data using Schlumberger's TDT, or thermal decay time log, as an example.
Virtually all current presentations of the pulsed neutron log data use a format very similar to the TDT-K display. TDT version K is not the newest tool, but until very recently it has been the yardstick against which others were measured. On the left track is the gamma ray curve, used to indicate sand shale lithology and correlate with open-hole logs. In this example, the gamma ray indicates clean sandstone to the left and shale to the right. The primary log measurements are shown to the right of the depth track. The neutron capture cross-section, or sigma curve, is scaled from -20 to 60 capture units. The ratio curve is the ratio of the count rates at the gamma ray detectors located nearest and farthest from the neutron accelerator. This ratio may be viewed as an uncalibrated relative indicator of porosity, with porosity increasing with increasing ratio. This particular curve shows a false decline in porosity in the presence of gas-filled formations. While the sigma curve is extended over 2 tracks, the ratio curve is confined to the center track. In the right-hand track is shown the overlay of the near and far detector count rates. While these are scaled to overlay one another in a water-bearing zone, the far curve moves to the left of the near curve in a gas-bearing zone. The degree to which this effect occurs depends upon the logging tool used. In this example, the oil-water and gas-oil contacts are clearly indicated. The formation sigma curve over the permeable formation shows the largest response in the water zone, a somewhat lesser response in the oil zone, and the least response in the gas zone. The ratio curve indicates a relatively uniform apparent porosity across the water and oil zones, and a sudden drop in apparent porosity in the gas zone. This effect is common to the neutron logs, and it indicates a decline in the hydrogen content of the formation rather than a porosity change.
All service companies show essentially the same curves in the same tracks. However, the curves of one service company cannot in general be compared directly to those of another. The spacing between the detectors is likely to be different, as is the way the electronic measuring gates are arranged. Therefore, count rates, ratios, and even sigma values may vary among service companies. If a pulsed neutron log is run to compare with earlier logs, it's best to use the same model tool that was used initially. It's also desirable to record a number of passes with the tool and compute a weighted average sigma response to minimize the variations inherent in the nuclear measurement. The newest pulsed neutron logs present numerous supplemental curves in addition to the basic ones described here, and they're covered more fully in your manual, as is the calculation technique for determining saturations from log data.
The applications of pulsed neutron logging may be categorized into 4 groups: evaluation of fluid saturations when open-hole data are not available, time-lapse logging to monitor changes in saturation over time, often useful in water floods to monitor flood front movement, secondary measurements that can indicate flow inside the casing, and a log-inject-log technique used to determine the residual oil saturation expected in a reservoir after it waters out. The log-inject-log procedure involves logging the well, injecting a brine of known contrasting salinity to displace all formation fluids except residual oil and rerunning the log, and then injecting formation water to displace the brine and rerunning the log a 3rd time. The residual oil saturation can be calculated from the porosity, log-determined sigma values, and actual sigmas for the 2 injected waters. There are a number of variations on this technique. When the formation waters are too fresh or are of mixed and therefore unknown salinities due to water flooding, a salinity-independent measurement, such as the carbon-oxygen log, is required. Instead of focusing on the gamma-ray count rate due to neutron capture, these tools analyze the gamma-ray spectrum emitted by the formation when it is bombarded with neutrons. Carbon-oxygen tools are capable of measuring the relative qualities of up to 8 elements, with the main interest being in the amounts of carbon and oxygen. 2 logging speeds are necessary due to the shallow depth of investigation and the low count rates associated with certain elements. Therefore, the tool must be run once at speed, and then again at either a series of stationary sampling stops or a reduced speed. The measured carbon-oxygen ratio varies as a function of porosity, lithology, and oil saturation. However, for some tools to accurately distinguish between limestone and sandstone formations, the ratios of various other elements must also be computed and compared. For example, with Schlumberger's GST tool at about 30% porosity, a water zone in limestone looks like an oil zone in sandstone. A computed carbon-oxygen log is shown in your manual. It is possible to measure porosity using cased-hole logging techniques. However, unlike pulsed neutron and carbon-oxygen logs, porosity through casing measurements are made with a tool that carries a neutron source downhole. Modern porosity through casing tools are configured with 2 detectors, one far and one near, in much the same manner as the pulsed neutron capture tools, and are generally called compensated neutron logs, or CNLs. CNLs are usually larger diameter tools not available in through tubing sizes, and are typically run decentralized to ensure better sampling of the formation count rates by minimizing the wellbore influence. Unlike the pulsed neutron tools, which measure the gamma rays emitted when slowed-down neutrons are captured, the CNL counts the slowed-down neutrons at the detectors. The number of slow neutrons at the detectors is a function of the number of hydrogen atoms in the fluid-filled pore space. And because this pore space is filled with hydrogen-rich water, or hydrocarbons, the number of hydrogen atoms is directly proportional to the porosity. Like the pulsed neutron capture tools, the ratio of the near and far detector measurements has to be calculated. This ratio is nearly linear for limestone and sandstone formations over normal porosity ranges. Porosity is presented directly on the log, typically on a limestone scale or occasionally on a sandstone scale. If the lithology is different from the scale used, corrections must be made. Corrections must also be made for the environmental effects of the borehole, including the open hole diameter, casing thickness, cement thickness, wellbore fluid weight, wellbore fluid salinity, formation water salinity, and wellbore temperature. Correction charts for these factors are available from the service companies.
The response of the CNL is very similar to the pulsed neutron tool ratio curve. The presence of gas in the pore space causes the tool to indicate an erroneously low porosity due to low hydrogen density. In shaly zones, the hydrogen atoms, in the form of water molecules attached to the shale matrix, cause an erroneously high porosity reading.
The third category of cased hole formation evaluation log is made up of tools that make natural gamma ray measurements. These instruments do not carry any radioactive material or neutron generation capability and include the gamma ray and natural gamma ray spectrometry tools. The source of natural gamma rays in rock formations is mainly traceable to three radioactive elements: thorium-232, uranium-238, and potassium-40. During their decay to other stable elements, each gives off gamma rays with energies characteristic of the parent element. Conventional gamma ray tools simply count all gamma rays, regardless of energy level, whereas the natural gamma ray spectral tools measure the amounts of gamma radiation within certain energy ranges to determine the relative contribution from each of the three elements. Most of the radioactive elements tend to concentrate in shales, and as a result, the gamma ray tool has long been a shale indicator. However, because uranium tends to form compounds which may be carried by water over great distances, uranium salts may be deposited along fractures and within permeable formations, giving an erroneous shale indication. Conversely, their presence can indicate useful permeability or fractures. If the gamma ray log is run in an area where the correlation of formation shale volume to gamma ray response is known, then the volume of shale in a sandstone may be calculated from the conventional gamma ray log. The horizontal axis of a shale volume curve is a measure of relative gamma ray deflection between the shale-free reading and the total shale point, and is given by the equation shown here, where GR log is the measurement at the point of interest. The computation of shale volume is carried out for 2 points on the example gamma ray log in your manual. In certain non-shaly formations that contain large amounts of uranium salts, causing false shale indications, the spectral gamma ray may be used effectively to infer fractured intervals. This example of a spectral gamma ray log from the Austin Chalk shows the individual potassium, uranium, and thorium curves along with the total counts measured by the conventional gamma ray tool. Note that the total count curve appears to indicate a very shaly interval from about 5,445 to 5,513 feet, 1,660 to 1,680 meters. However, it is clear from the potassium and uranium curves on the log that this zone is not very shaly, and that the total count reading is primarily due to uranium counts, perhaps an indication of fracture permeability.
So we see that under the heading of cased hole formation evaluation, we have three basic types of tools. The pulsed neutron capture and carbon-oxygen tools, which measure the gamma ray response to the bombardment of the formation by neutrons, thereby helping us determine fluid saturations. The CNL, which measures the ability of the formation to slow down neutrons and indirectly measures its porosity, and the gamma ray logs, which measure the natural gamma rays generated by the shale in the formation and thus the relative amount of shale present. All of these tools rely on nuclear measurements which are relatively uninhibited by the casing and cement. And when used together, they can reinforce or discount interpretations made from the individual tools alone. In the next unit, we shall investigate the use of cased hole logs to evaluate the integrity of the casing and cement. For now, please read sections 1 and 2 in your manual and work the appropriate exercises. Well integrity logs for the evaluation of cement and casing conditions include the cement bond and casing inspection tools. The cement bond tools include the cement bond log, the well-bore compensated cement bond log, the pad-type cement bond log, and pulse echo tools. All of these are acoustic devices which evaluate the amount of annular cement around the pipe. Casing inspection tools include mechanical, acoustic, electromagnetic, and electropotential measuring tools. Mechanical tools can make measurements only inside the casing, while the others are capable of evaluating both the inside and the outside of the casing. Some of these, especially the mechanical tools, are used to inspect the intermediate strings of pipe for drill pipe wear resulting from deeper drilling. All of these tools are likely to be used to examine the casing in the producing interval for evidence of corrosion or deformation.
The casing inspection devices used to inspect the production string are all too large to be run through tubing. Similarly, most of the cement bond tools are too large to be through tubing devices. But since the usual application is to run these tools before installing the tubing, size is generally not an issue. The cement bond log, or CBL, is an acoustic device used to detect the presence or absence of a cement bond between the casing and formation. The tool includes an acoustic transmitter and usually 2 receivers located 3 feet and 5 feet, 0.91 and 1.52 meters from the transmitter. The tool, which must be well centered, emits an acoustic signal that is detected by these receivers after traveling one of 4 possible acoustic paths from the transmitter to the receiver. The signal through the casing is likely to be the fastest, since sound travels quickly through steel. As a result, it is the first of the 4 signals to arrive at the far receiver. The next signal to arrive is that which passes through the formation. The cement signal, and finally the fluid signal, arrive later. Cement contacting the casing tends to dissipate or attenuate the signal energy as the signal propagates through the pipe. The greater the area of cement contacting the pipe, the weaker the signal at the receiver. The effect of a good cement job on the received signal, therefore, is to cause the pipe portion of the signal to be weak, while the formation portion is strong. When no cement is present, the free pipe rings rather loudly, like a bell, resulting in a very strong signal. The amplitude curve is universally presented on CBLs and typically displays the amplitude of the first signal to arrive at the near receiver. Since this amplitude is for the pipe portion of the signal, a low amplitude indicates good pipe to cement bonding, while a high amplitude indicates poor bonding. The amplitude signal alone, however, does not reveal the quality of the cement bond to the formation. The variable density log, or VDL, helps in that regard. Also displayed on the CBL, it is made up of numerous closely spaced exposures of the film by the positive wave train amplitudes. The result is a sort of contour map of the history of the wave train over the logged interval. Notice that the pipe portion of the received acoustic signal appears as strong straight lines. The formation signal, on the other hand, appears at different times, since the cement thickness and formation acoustic properties change from one point to the next. In an interval with a very good bond, the pipe portion of the VDL does not show up because the amplitude of the wave train is too low to expose the film. The formation signal, however, comes in strongly. A reduction in wellbore pressure from the time the cement hardens to the time of the CBL logging run can cause the pipe to shrink from the cement sheath, forming a microannulus around the casing. Even though this microannulus does not permit hydraulic communication, the cement cannot maintain the coupling to the pipe required to attenuate the acoustic signal. As a result, the recorded amplitude will indicate a poor bond. However, during logging, if the internal pipe pressure is increased above the curing pressure, the microannulus will be closed and an interpretable log will result. The travel time curve is the primary quality control curve on a CBL. Travel time is measured from the initiation of the acoustic signal at the transmitter to the arrival of the first signal at the near receiver, which reaches a minimum amplitude level. When the signal is reduced, due to a good bond, the travel time signal stretches, since the minimum amplitude level is not reached until a later time. This is known as cycle stretch. If the pipe signal is very low, the first arrival may not reach the minimum amplitude level, but the second or later positive arrival may do so. This is known as cycle skipping. Neither of these effects should be of concern, since they relate to a condition of good bonding.
However, shortened travel time can also indicate that the tool is not properly centered, and that the acoustic signal is traveling to the receiver faster through the shorter path on the side closer to the casing wall. Such a situation will result in an inaccurate log. Even if the tool is centered, very low porosity limestone or dolomite formations have faster travel times for an acoustic signal than steel pipe, perhaps by as much as 12 microseconds. In such cases, the formation signal beats the pipe signal to the receiver, and a shorter travel time is recorded. Thus, the pipe-to-cement bond cannot be measured in fast formations.
If a partially cemented section of casing produces an amplitude higher than the minimum amplitude measured in a well-cemented zone, a hydraulic seal may or may not exist. The bond index can help in this regard. The bond index is defined as the signal attenuation in the zone of interest divided by the attenuation in a zone with known good cementation. If the bond index is 0.8 or better over an interval of pipe, a reasonable assurance of hydraulic isolation is possible. The interval length of 0.8 bond index required for a variety of pipe sizes is anywhere from 5 to 15 feet, 1.5 to 4.6 meters. The larger the casing size, the longer the interval needed to ensure hydraulic isolation.
The equation for the bond index is expressed in units of decibels per foot, while most amplitude curves are presented in millivolts or percent-free pipe. Most service companies have charts to convert from millivolts to decibels per foot, and vice versa. An example is given in your manual. Note also that some tools, like Schlumberger's fluid-compensated CBT, incorporate technology that automatically provides readings in decibels per foot. Your manual also discusses the differences among the following: the typical CBL, the well-bore compensated CBL, the pad-type CBL, and the pulse echo CBL. Now let's consider the second major category of well integrity logs, the casing inspection or corrosion logs.
These logs include mechanical, electromagnetic, acoustic, and electropotential measurements. They are used to monitor pipe wear caused by continued drilling operations, detect corrosion on the inside or outside surfaces of the pipe, locate holes and pits, detect split or parted pipe, detect collapsed pipe, locate perforations, and detect electrochemical corrosion. The tools for these logs are through casing tools, not through tubing, and are generally sized to match the casing to be inspected. Mechanical calipers are of two basic types. The bowspring type caliper is typically run with a flow meter. It is often used to monitor chronic problems such as asphalt, paraffin, or scale buildup inside the casing. It is also routinely used in open-hole completions, where a flow profile using a flow meter is required. The second type of mechanical caliper is the multi-finger type, with anywhere from 40 to 80 individual fingers. As these fingers scrape the pipe wall, their maximum deflection is monitored. A single measurement of the maximum deflection among all the fingers is most common, although some tools are capable of providing a maximum and minimum indication. The electromagnetic tools fall into two categories: pad-type tools, which measure the distortion of a magnetic flux around a casing defect, and phase shift tools, which measure the amount of casing metal by measuring the phase shift between two electromagnetic coils. Both types of tools inspect both the inside and the outside of the pipe. Inside the pad-type tool is a coil which generates a magnetic field whose flux lines are parallel to the casing axis. Inside each pad is another coil. When a pad passes over a point where the flux lines are distorted into the wellbore, the coil in the pad generates a current. This occurs at a pit or hole in the pipe, even if the pit is located on the outside of the pipe. Surface roughness has the same effect, appearing as a multitude of pits. These tools have an upper and lower array of pads to ensure complete coverage. The tracks labeled FL1 and FL2 on the log are the pad array measurements. The track labeled discriminator shows the measurement of the internal wall condition. In this example, the interval from 4,793 to 4,870 feet, 1,401 to 1,484 meters, shows general external corrosion, since the inner wall is clear of defects, except for the two intervals here. The track labeled average shows the average of all the FL1 and FL2 responses as seen by the pads. If the defect is large, it is detected by many or most of the pads and therefore shows a large average. A single point defect shows a small average reading. The phase shift devices operate differently from the flux distortion devices. These tools have a transmitter coil carrying an alternating current that causes a magnetic field to be formed around the coil. The lines of this field cross through the casing and induce a current in a receiver coil located below the transmitter. The current induced in the receiver coil will be out of phase by an amount that is proportional to the amount of metal the field lines cut. Problems with this measurement are that it does not distinguish small defects very well, and that it responds similarly to corrosion on inner and outer surfaces of the pipe. Often, therefore, an internal electronic caliper is included with this device to distinguish inner from outer surface damage. This example illustrates the response of a phase shift device. Note that the phase shift generally increases with increased weight casing, and that a collar or defect shows up as two distinct peaks, resulting from the field lines passing over the collar or defect twice as the tool moves up the well bore. Casing potential surveys detect electrochemical corrosion as it occurs by measuring the galvanic voltage it sets up. Those sections of the casing that act as anodes are undergoing electrochemical corrosion and metal loss. Casing potential surveys locate these intervals and indicate where cathodic protection can help to protect the casing. They must be run in an empty hole or in oil or gas. A conductor such as water or mud will provide a short which precludes interpretation. The resulting log is a recording of the small galvanic current present within and external to the casing when corrosion is taking place. A positive slope, or increase in voltage with decreasing depth, indicates a cathode, and a negative slope indicates an anode. The presence of an anode corresponds to an interval of metal loss. This log shows the potential profile for a 1,000-foot casing interval. Run 1 indicates that the interval from 1,495 to 1,650 feet, 456 to 503 meters, and from 1,700 to 1,850 feet, 518 to 564 meters, were anodes, and hence corroding. Subsequently, cathodic protection was provided by putting a 5-amp current to the wellhead. Run 2, the second casing potential survey, shows that one area still remained anodic. At 8 amps, Run 3 shows that the whole casing string is now a cathode, and electrochemical corrosion is eliminated. The acoustic casing inspection tools, basically modifications of the pulse echo cement bond tools, are discussed in your manual. Also found in your manual is a description of the borehole televiewer, which utilizes an ultrasonic transmitter to produce an image of the borehole or the casing inner wall. These tools require a fluid-filled borehole. Video cameras have also been adapted for downhole use and can provide an image in boreholes filled with air or clear liquids.
In Unit 2, we have covered the two basic categories of well integrity logs. Cement bond logs, which are acoustic tools used to determine the existence of cement bonding to the casing and formation, and casing inspection tools, which use mechanical, electromagnetic, or electropotential measurements to determine the condition of the casing ID and OD. In the final unit of this module, we shall describe the cased hole logs used to evaluate flow in or behind pipe. For now, please read Section 3 in your manual and work the appropriate exercises. In this unit, we look at the techniques for measuring flow in or behind casing. These techniques can be qualitative or quantitative. The basic qualitative measurements used to evaluate fluid movement include temperature surveys, noise logs, and radioactive tracer surveys. Quantitative techniques also include radioactive tracers, but most commonly rely on flow meters or the newly developed oxygen activation log. First, let's investigate the qualitative devices.
Generally, deeper formations are hotter than shallow ones, resulting in a geothermal gradient of about 0.5 to 2.0 degrees Fahrenheit per 100 feet, or 1.0 to 3.7 degrees centigrade per 100 meters. While it may actually vary somewhat with depth, for our purposes the gradient is assumed to be linear. Temperature surveys measure the difference between the fluid temperature within the casing and the geothermal gradient, and are used to locate fluid entries in producing wells and fluid exits in injection wells. For example, liquid flowing into the wellbore from the formation enters the wellbore at essentially the same temperature as the formation. As the liquid moves uphole, its temperature gradually begins to decrease as it loses heat to the surrounding cooler formations, approaching the geothermal gradient. In general, this geothermal gradient will be displaced to the right as the flow rate increases. Looking at gas entry for the same completion geometry reveals that the point of gas entry shows a cooling effect due to the expansion of the gas. As the gas moves uphole, it is heated until it crosses the geothermal gradient and begins to cool above that point. The magnitude of the entry point cooling effect depends on the pressure drop, which in turn depends on the gas flow rate and the formation permeability. Lower pressure drops will give less of an effect. The temperature log, when run with other surveys such as the flow meter and a fluid identification device, may also be effective at detecting channels behind pipe. In our example, produced fluid is being supplied up a channel, below the casing perforation. Since the static fluid below the perforation is in thermal equilibrium with the produced fluid in the channel, the temperature survey will indicate a fluid entry here. The accompanying flow meter will indicate a fluid entry here. The discrepancy is explained as follows. Since the temperature log detects changes both inside and outside the casing, it shows the actual depth of entry from the formation. The flow meter detects fluid movement only inside the casing, so it shows where fluid is entering the wellbore at the perforation. Based on these facts, a behind-pipe channel is a reasonable explanation for the conflicting information. In the case of a channel above the perforation point, the flow meter again shows the entry point into the wellbore. The temperature survey indicates cooling there and suggests a gas entry. But the temperature survey also indicates another point of cooling. When the fluid identification device confirms that the produced fluid is a liquid, the confusion is explained as a channel from above.
Indeed, if the flowing temperature in the wellbore is above the geothermal gradient, every entry uphole, whether a gas or a liquid, would be a cooling anomaly. Therefore, the use of combination tools with at least a flow meter, temperature survey, and fluid density measurement device is necessary to examine multi-phase flow downhole.
Temperature surveys are also used in injection wells to identify the intervals taking fluid. The technique entails running a pre-injection base survey, running a temperature survey while injecting the cooler surface liquid, shutting in the well, and then running a number of temperature surveys during shut-in. The volume of injection fluid left in the wellbore after shut-in will return to the geothermal temperature relatively rapidly, while the large volume of injected fluid held in the zone of injection will warm to the geothermal temperature much more slowly. As a result, the shut-in temperature surveys develop a bump across the injection zone, highlighting its extent.
For water injection, at least a 10-degree Fahrenheit or 5.6 degrees centigrade difference between the injected fluid at the sand face and the geothermal temperature is required for good development on a 48-hour shut-in survey. If a 20-degree Fahrenheit or 11.1 degrees centigrade difference exists, then the bump will develop as quickly as 12 hours after shut-in. This technique is effective regardless of how the injected fluid gets to the zone, through the casing or behind it. Once the well is shut in, the fluid movement downhole should be stopped completely before logging to ensure accurate results. The same principle may be used to determine fracture height and acid placement.
The Radial Differential Temperature Survey, or RDT, evaluates the presence of active channels behind pipe. The measurement is made with a centralized, stationary tool. With the two arms of the tool touching the wall of the casing, the tool rotates and measures the temperature difference between the two arms. If a channel is present, it will be cooler or warmer than the surrounding geothermal temperature, and therefore the anomaly will repeat after 360 degrees of rotation. The log itself is a presentation of the temperature difference plotted against the degrees of rotation. For example, measurements made at 4,656 feet, 1,419 meters, with the well flowing and then shut in, and at 4,590 feet, 1,399 meters, also flowing and shut in, confirm that fluid movement exists behind pipe, and that fluid from the upper zone is in communication with the wellbore.
The second category of qualitative fluid movement detection devices is the borehole noise survey. Noise surveys detect fluid flow downhole by the sound it generates. Noise logging tools detect noise generated either inside or outside of the wellbore, and most are designed to be run in a stationary mode. Both fluid movement and pressure drop are required for the noise to be generated.
Noise amplitude is greatest at the point of entry from the formation and at the point of restriction of flow. Entry back into another formation also generates some noise, but less than the other examples, since the pressure drop is small. Detailed analysis of the noise spectrum has shown that different flow conditions downhole often have unique characters. In general, single-phase flow entries tend toward the higher frequencies. Each trace on the log corresponds to the noise energy at levels greater than that indicated. For single-phase flow, the log curves are tightly packed at the entry point. Bubbly two-phase flow shows a very different character and tends to be confined to the lower frequency portion of the noise spectrum. The 200, 600, 1000, and 2000 Hertz curves are spread out, indicating much energy in the lower frequency bands. Also, the noise energy remains high above the entry point, because the source of the noise is not just the entry point pressure drop and flow, but the turbulence generated by the passage of the bubbles above the entry.
The signal detected by the noise tool is strongest when the tool is in liquid. If the tool is brought up above the gas-liquid interface in the casing, acoustic decoupling occurs, and the amplitude of the noise detected is considerably lower. Furthermore, the noise level for a point source of entry weakens as the tool is moved away from the source, with the higher frequencies weakening more rapidly than the lower frequencies.
The third technique for qualitative determination of fluid movement involves injection of radioactive material and subsequent gamma-ray logging. Radioactive tracer techniques are used primarily to determine fluid movement into injection wells and to locate the placement of injected material, such as fracture proppant. The tracer may be added to the injected fluid at the surface or released downhole. For liquids, the most common radioactive isotope tag is iodine-131, introduced as sodium iodide dissolved in water. Iridium-192 is often used for tagging sand or proppant. The use of multiple radioactive materials within a single application has been developed in recent years. Typically, different isotopes are used to tag different materials, perhaps the fracturing fluid, lead-in sand and tail-in sand of a fracture treatment, and their relative placement is evaluated later using a spectral gamma-ray tool which can distinguish among the isotopes. The most common tracer technique detects the presence of channels behind pipe. Radioactive material is ejected from the tool into the injection flow stream above the perforations. The tool is lowered and the interval logged from the bottom to the top. The location of the ejected cloud of radioactivity is easily detected. The tool is again lowered and another log made while injection continues. With each repeated log, the movement of the isotope is monitored. If an upward channel exists, the isotope or part of it changes direction and begins to move uphole. Fracture height determinations are made by tagging the injected proppant and then comparing pre- and post-fracture gamma ray logs to detect its location. A pre- and post-fracture temperature survey confirms the fracture location. The increase of radioactivity at the bottom of this interval is attributed to the settling of proppant in the rat hole. The apparent discrepancy between the temperature and tracer techniques at the bottom of the fractured interval may be caused by the responsiveness of the temperature survey to the gross fracture height through which the fluid moved, part of which apparently remains unpropped.
All of the techniques discussed so far, temperature surveys, noise logs, and radioactive tracer logs, help us to qualitatively determine the entry point of fluids, the existence of channels, and the location of injected materials. However, they are not quantitative in that they do not tell us how much fluid is flowing into or from any given interval. Quantitative techniques include the use of radioactive tracers in injection wells, a technique which is covered in your manual, and more commonly, the oxygen activation log and turbine flow meters. These devices may be utilized for injection or producing wells, and we shall discuss them next, beginning with the oxygen activation log.
The oxygen activation log is a recent application of pulsed neutron technology to the problem of water flow detection. This device operates on the principle that the activation of oxygen nuclei by a burst of high-energy neutrons results in the emission of high-energy gamma rays at a measurable rate, a rate which declines as the radioactive isotopes created by the neutron burst decay. Activated oxygen decays at a predictable exponential rate. In order to determine if the activated oxygen is moving or stationary, the measured decay is compared to the predicted decay rate. This is done by comparing the gamma ray counts at 3 detectors spaced along a logging tool. The flow velocity, and hence the volumetric flow rate, is determined from the source to detector distance and the time at which the activated water passes the detectors. The device can be configured to measure both upflow and downflow, inside and outside the casing, and is sensitive to flow velocities from 2 feet per minute to 200 feet per minute, or 0.6 to 60 meters per minute. There are 2 basic types of flow meters: continuous flow meters, which are logged across the producing interval and include both small diameter and full bore devices, and the diverter flow meter, which diverts the flow through a narrow test section. Before we describe their operation, however, let's first review the behavior of formation fluids in the wellbore to better understand the physics of flow measurement. Here are the volumetric flow rates downhole. Volumetric flow rates at the surface are generally higher due to an increase in total fluid volume. The change is mostly due to the dissolution of gas from the liquid phases and the expansion of the gas. Because gas is far more soluble in oil than water, it is the rapid expansion of oil solution gas volumes which change the volumetric flow rate. As the oil is produced to the surface, the point at which the gas begins to break out of solution is called the bubble point. Gas that comes out of solution is called solution gas, while gas produced from the formation is termed free gas. The dramatic changes in gas volume are a function of gas gravity as well as pressure and temperature. The relation between the downhole and surface volumes is called the formation volume factor, defined as the oil or gas volume at reservoir conditions divided by the volume at standard surface conditions. The oil formation volume factor is typically about 1.0 to 2.0, and the gas formation volume factor is often expressed as its reciprocal, which has values in the hundreds. These values are determined from laboratory tests done on retrieved samples or from correlations with simply measured fluid properties. A full description of these concepts and techniques may be found in the video library module PE406, Reservoir Fluids, Sampling and Analysis. If free gas, oil, and water are present in the flow stream, various flow regimes may result. If the flow is water and oil, a bubble flow regime is most common. When gas and liquid are present, the flow is much more complex. Bubble flow probably exists up to a condition of about 10% gas by volume. A transition then quickly occurs to slug or more complex flow patterns. Unlike oil-water flow, gas-liquid flow is very turbulent and violent and produces a very complex response in the flow meter. As a result, gas-liquid flows can be difficult to measure accurately. The two terms used in vertical flow measurement, hold-up and cut, are often misunderstood. Cut refers to the amount of a particular phase that is being produced. For example, if 1,000 barrels per day, 159 cubic meters per day, of liquid is produced, and 350 barrels of it are water, the result is a 35% water cut and a 65% oil cut. Hold-up, on the other hand, refers to the fraction of the wellbore bulk volume occupied by one of the phases. For example, if we have a standing water column in the well with oil above, and we flow oil into the wellbore, the oil will bubble up through the water and flow out the top. We would have a 100% oil cut at the surface, but across the bubbly interval, the oil bubbles might occupy only 30% of the volume, and that interval would have an oil holdup of 30% and a water holdup of 70%. Because of the density difference, water is likely to accumulate downhole in all wells, even when the water cut is small. The difference between the cut and holdup can be dramatic, especially at low rates. At 300 barrels per day, 48 cubic meters per day, a 1% water cut at the surface may mean a 50% water holdup downhole. Measurement of phase holdup is done using a gradiometer, which measures the bulk density of the fluid over a 2-foot interval. This is done by measuring the pressure difference over that interval with a mechanical or electrical gauge, or by using a nuclear device which relates the rate of gamma ray penetration through a fluid to its density.
It's not uncommon to run other tools for additional pressure analysis, like this production pressure tool, or PPT, with side port entries and quartz pressure transducer. We understand then that in order to measure the downhole rate, we must know something about the relative volumes of phases flowing at downhole conditions. We can gather that information with a gradiometer survey run on our flow meter. But what does our flow meter measure?
Flow meters respond to the bulk flow rate, even in multi-phase flow. A turbine or spinner rotates as a function of the rate at which fluids flow past it. If the spinner response in a static fluid is plotted in revolutions per second for several logging speeds, both up and down, the relationship is linear. The lines do not, however, go through the origin. The cause of this shift is the viscosity of the fluid. Greater viscosity tends to cause a greater shift. When the spinner encounters an upflow, as would be expected in a producing well, the effect is to shift the response curve of the tool to the left by an amount equal to the upflow velocity.
The flow velocities measured are those seen by the spinner turbine blades. If the spinner is centralized, and it should be for best results, it has sampled the flow from the center of the well bore, but too high, which is not representative. As a result, a flow profile correction factor must be used, typically 0.83.
To compute the bulk flow rate in barrels per day or cubic meters per day, one must multiply by the proper conversion factor and wellbore ID squared. The cumulative bulk flow for different entry points is determined by difference. For multi-phase flow, once the bulk flow rate and holdup of the phases are measured, the slippage velocity of the light phase through the heavy phase must be determined. The relationship for slippage velocity is a function of holdup and fluid density difference. For example, for an oil density of 0.7 grams per cubic centimeter, a water density of 1.0 grams per cc, and a water holdup of 0.70, the slippage velocity of the oil with respect to the water is about 19 feet per minute, 5.8 meters per minute. When dealing with a gas-liquid system, a slippage velocity of 60 feet per minute, 18.3 meters per minute, can be assumed. The computation of real flow rates for multi-phase flow, using these values of bulk flow rate, holdup, and slip velocity, is shown in your manual for both oil field and metric units. Deviated wells with multi-phase production pose a unique problem because the oil or gas tends to gravitate to the pipe's high side and the water slides down the low side, giving the appearance of downflow. This problem can be minimized by the use of a diverter-type flow meter, which expands an element to force the flow through a funnel-shaped test section. The response of the diverter flow meter is pre-calibrated, and each tool and spinner combination has a unique calibration curve obtained from the bender. Often these tools also contain a fluid identification device.
So we see that the downhole flow can be quantified and allocated to specific perforated intervals using flow meters. Multi-phase flow is more complex than single-phase flow, and identifying the volume of individual phases becomes important. In deviated wells, the density differences among oil, gas, and water require special tools to accurately measure flow. If we wish a qualitative indication of flow, we can rely on temperature or noise measurements. In injection applications, tagging an injectant with a radioactive isotope and using a gamma ray log to chase it can tell us where it went. This unit completes our module on cased hole logging. Please read sections 4 and 5 in your manual and work the appropriate exercises. Good luck.